Assalamualaikum and greetings. We are from Group 14 and we will present about design of reactor-separator system for methanol production plant. And this is my team member that will present alongside me. My team member consists of Tang Wen Ting, Sia Ling Hui, one Ahmad Hakim, one Ahmad Syakir Alwi, and me myself, Ku Muhammad Amir Syahrif. Methanol is an important industrial chemical widely used in the production of formaldehyde, with growing demand in both the chemical and energy sectors. It is produced through the catalytic hydrogenation of synthetic gas, which consists of carbon monoxide, carbon dioxide, and hydrogen. This reaction is highly exothermic and equilibrium limited, making reactor design very important to ensure effective heat removal, high conversion, and good selectivity. However, the reactor effluent contains impurities, which means further purification is required to achieve at least 99.5% methanol purity. While distillation is commonly used, it is very energy intensive. Therefore, this study proposed an absorption-based separation process as a more energy efficient and selective alternative. For the reaction engineering part, the objectives are to propose a suitable industrial methanol production route and justify its selection, to identify the main and side reaction involved, and apply kinetic data to evaluate reaction rates and reactor performance. For separation process, the objective include identifying the composition of the crude methanol stream, designing an absorption-based purification system to achieve 99.5% purity, and selecting appropriate absorbance and operating conditions.
Assalamualaikum and hi, my name is Ahmad Hakim Ahmad Safran, and today we are looking at the industrial design of reaction process system centered on steam methane reforming or SMR and low pressure methanol synthesis. For technology and feedstock, SMR is an industrial benchmark for a reason. It has been commercially refined since 1960 and offer a highly predictable safety profile. And when we are looking at the feedstock, natural gas is our ideal choice. It provides high carbon content and robust global availability, supporting maximum conversion efficiency. From a sustainability standpoint, SMR is actually more carbon efficient than electro roads. It minimizes the waste of carbon sources and keep operating low cost because it's requires significantly less electricity than electrolysis. And for energy and thermal integration, our system is designed for high energy recovery. We utilize an isothermal reactor that functions as a heat exchanger, and the exothermic heat generated during the methanol synthesis isn't wasted. It is efficiently captured to produce methane pressure steam for use elsewhere in the process. Next, we are looking for the reaction involved in this methanol synthesis. So, the reaction involved is three primary pathways. First is hydrogenation of carbon monoxide, where carbon monoxide react with hydrogen to produce methanol, and the activation energy is 60.5 kilojoule per mole, and the Arrhenius constant is 1.07 times 10 to the power of 12. Next is hydrogenation of carbon dioxide, where the carbon dioxide will react with the hydrogen and produce methanol and the byproduct, which is water. And there is a water gas shifting reaction where the carbon monoxide react with the water to produce carbon dioxide and hydrogen gas. And there we are using Lamar-Hinshelwood kinetic to determine the rate of reaction and utilize the Arrhenius equation for the different temperature that we are using in the simulation. Now we are looking at the process flow diagram, and we are using symmetry simulation to simulate this plant. First, we have a few components that we using in this simulation. We have a mixer to mix the multiple stream, and we use heater to heat up the stream. And next, we have a few conversion reactor and the equilibrium reactor to the convert the reactant to produce a desired product, and we have cooler to cool down the reactor, and lastly we have PFR to produce the methanol in this plant. Okay. This is the production of syngas, which is a gas of carbon monoxide, carbon dioxide, and hydrogen. And first, we are mixing these two stream, which is steam and methane. We mix these two stream and we heat it up into a certain temperature, and we want go to the conversion reactor and equilibrium reactor to convert the natural gas into a syngas. Then we have a secondary reaction which we add the air and water to complete the conversion of methane into the syngas. And the final product that we are looking is the carbon monoxide, carbon dioxide, and the hydrogen gas produced at the part at the last part of this production, which is at S10. Next, we are looking at the production of methanol, where this is the most important part because this is where the methanol start to produce. So we run into a cooler to cool down the previous stream, which has a temperature of 970 degrees Celsius and decrease into 300 Celsius. And then we run to a PFR. PFR is a type of continuous reactor where reactant flow in one direction through a tube, and there is no mixing occur along the flow direction, but we assume to complete mixing across the cross section. And this reactant move as a plug into the reactor, and the concentration and temperature change gradually from the inlet to the outlet, and there is no back mixing, and the high conversion can be achieved for this reaction.
Hi, my name is Ahmad Syakir Alwi, and I will continue for the reaction engineering part. We are going to choose the type of reactor, and we will use the Levin spill plot. Using the Levin spill plot, we find the volume for the CSTR and PFR reactor. So, according to our calculation, the volume for CSTR is 15.836 and PFR is 3.99 meter cube. This make that our chosen reactor is PFR because it has the smaller volume than the CSTR. Other than that, PFR also offer other advantages such as the reactant concentration is highest at the inlet and decrease gradually. It is also better suited for catalyzed process and help prevent catalyst sintering. As for our assumption for the calculation, we assume that the reactor is steady state operation and also undergo perfect mixing. For our operating condition, our reactor operate at isothermal operation at 300 degrees Celsius. It is optimized for high catalytic activities and also enable efficient processing of 11,293 kilomole per hour feed. The exothermic heat is then recovered for steam with high pressure generation. For our operating pressure, our reactor operate at 90 bar. The high pressure shift equilibrium for methanol formation, and it increased gas density for compact reactor. The higher partial pressure of uh, hydrogen gas and carbon monoxide improve the reaction rate and also support high conversion efficiency. For our residence time is around 2.47 seconds, which is very short contact time, achieve high carbon monoxide conversion, minimize secondary reaction, and reduce reactor size. For our catalyst, we use three catalysts, which is copper, zinc oxide, and aluminum oxide. Copper is used for active site for hydrogenation. Zinc oxide is used to prevent sintering, increases surface area. Aluminum oxide provides mechanical strength and thermal stability. All of three catalysts is industry standard for low pressure methanol process. For material balance, the inlet for our reactor is around 11,293 kilomole per hour. And the outlet for our reactor is around 9,582 kmol per hour. The methanol produced is around 855 kmol per hour, which translates to 171,000 ton per year for 261 day working for 261 working days per year. For the process optimization, higher pressure favors methanol synthesis and also improve methanol yield and overall efficiencies. For residence time, adjust the flow velocity to optimize contact time and also ensures maximum reactant conversion and also prevent excess water accumulation and also reduce inhibition. For temperature pressure time balance, precise control enhance reactant performance and maintains catalyst activity and stability.
Hello, I'm Wen Ting. So I will be presenting chapter 3, separation process for methanol production. So first, I will start with identification of species and concentration of impurities in the crude methanol stream. After the reactor, the crude methanol stream does not contain pure methanol. So the main product is methanol, which is the desired chemical, but there are also impurities present, with water being the major impurity form during the reaction process. So besides water, there are also unreacted gases such as hydrogen, carbon monoxide, and carbon dioxide. So these gases remain due to incomplete conversion in the reactor. And besides that, inner gases such as nitrogen and methane may also be present in the stream, and these gases do not participate in the reaction but are carried along from the feed and upstream process. So based on the concentration analysis, water has the highest impurity concentration and making it the main target for removal in the purification stage. So the concentration of this species is calculated using the ideal gas law Ca equal to Ya Pt over Rt, and the results are summarized in this table. So next, I will discuss the strategy to achieve 99.5% methanol purity using an adsorption-based purification system. So the purification system consists of three main steps. First is the flash separator. So in this unit, gas-liquid separation occurs, and the lighter gases such as hydrogen, carbon monoxide, carbon dioxide, nitrogen, and also methane exit from the top of the separator. And meanwhile, the crude methanol mixture, which contains methanol, water, and impurities exits from the bottom. So this step can help to reduce the load on the adsorption unit and improve separation efficiency. So the second step is the adsorption column, which is the main purification unit. So in this study, molecular sieve zeolite 3A is used as the adsorbent. So the crude methanol stream flows through the packed bed where water molecules and trace impurities are selectively adsorbed onto the surface of the zeolite. So this process significantly improves the methanol purity. And besides that, the adsorption process operates at temperature between 30 to 60 degrees Celsius and 10 to 30 bar. So these conditions are suitable for efficient adsorption and stable operation. But after some time, the absorbent will become saturated and need to be regenerated. So this leads to step 3, which is adsorbent regeneration using TSA, temperature swing adsorption. So in this step, heated gas is passed through the adsorbent bed at 150 to 250 degrees Celsius. So this can remove the adsorbed water and impurities from the zeolite surface. So the system then cools down before being reused. So the regeneration process can allow continuous operation and increase the lifespan of the adsorbent. Next, I will discuss the adsorbent selection and process conditions. So the molecular sieve zeolite 3A is selected due to several advantages. First, it has high selectivity towards water, which is the main impurity present in the crude methanol stream. So it is specifically designed to preferentially adsorb smaller and highly polar molecules such as water, while allowing larger methanol molecules to pass through. So this can ensure that the water is effectively removed without significant loss of methanol. Second, it has a uniform pore size and well-defined crystalline structure, which can enhance selective adsorption. So this uniformity allows consistent separation performance and improves the efficiency of the purification process. And besides that, it has high adsorption capacity, enabling them to remove the water to very low concentration. So this makes them highly effective for deep dehydration, and suitable for achieving industrial-grade methanol purity. And furthermore, the adsorbents are regenerable and energy efficient, so once the adsorbent becomes saturated, it can be regenerated by heating, reducing the need for frequent replacement and lowers the operating cost. So the operating conditions for adsorption are 30 to 60 degrees Celsius and 10 to 50 bar per joule. And meanwhile, the regeneration is performed at 150 to 250 degrees Celsius to restore adsorption capacity.
Hi, I'm Ling Hui. For the adsorbent requirement estimations, the main impurity in the cool methanol stream is water, and it must be removed to achieve a product purity of at least 99.5%. By using the backward calculations, the total water removed is at 3442.39 kg per hour. Molecular cis-3A is selected as an adsorbent. It is a zeolite with an LTS structure and a pore size of around 3 angstrom. This enables it to selectively adsorb smaller water molecules while excluding larger methanol molecules. It also has high hydrophilicity and good regenerability, making it suitable for the industrial use. For the adsorption isotone models, the Langway isotone is applied. This model represents type 1 adsorption behaviors, which correspond to the monolayer adsorption on a homogeneous surface, typical for microporous material like zeolite 3A. Based on the literature, we assume methanol does not interfere with the adsorptions. The adsorption sites are uniform, and the maximum capacity from literature is applicable. The isotone graph includes show that the adsorption capacity increases sharply at the low water partial pressures, and then reach its maximum capacity as the adsorbent becomes saturated. This characteristic curve confirms Langway type behaviors, supporting the use of these models. For the adsorption capacity, a working value of 0.2 kg water per kg adsorbent is used. Using a cycle time of 1 hour, the required adsorbent mass is 417211.95 kg per cycle. After applying a safety factor of 1.2, the final requirement is 500654.34 kg per cycle.
Next, moving to the conceptual design of the adsorption column. A feedback adsorption column is selected due to its simplicity and reliability. To ensure the continued operations, a dual column system is used. One column operates in the adsorption mode, and another one undergoes the regenerations. The system operates in the gas phase, which is suitable for the deep dehydrations. For the design basic, the back aspect ratio L over D is 3, the mass transfer zone is 0.15 meters, and the yield factor is 0.85. The mass transfer zone represents the region where the active adsorption occurs along the bed length. From the design calculations, the column diameter is 0.05 meters, and the column height based on the use factor is 1 meter. So the final column dimensions is a diameter of 0.05 meters and height of 1 meter. This configuration ensures the enough contact time and the efficient removal of the water. Finally, for the regeneration strategy, a temperature swing adsorption is used because the water is strongly adsorbed onto the molecular cis and cannot be effectively removed by the pressure reductions. The regeneration operates at a temperature between 150 to 250 degrees Celsius and consists of a three-main step. The first step is heating. A hot inert gas or the dry methanol vapors is used to break the interactions between the water and the zeolite. The second step is purge. The dry gas flows in a counter-current directions to remove the dissolved waters and prevent the readsorptions. The final step is cooling. The cool dry gas restores the adsorption capacity for the next cycles. For the continued operations, a dual column system is used. This swing operation ensures that the process runs without the interactions. Last, for the key advantages of this system are it can achieve the deep dehydration out to 99.5% purities. The adsorbent is reusable with a long lifespan, and it provides a high regeneration efficiency. So, in conclusions, this made the overall system reliable, efficient, and suitable for the industrial methanol purifications.
Now I will present the conclusions for both the reaction engineering and separation process. Starting with reaction engineering, the integration of steam methane reforming with low pressure methanol synthesis has been identified as the most technically and economically viable production route. This approach efficiently converts natural gas into synthesis gas, which is then further processed into methanol using well-established industrial technology. In terms of reactor selection, the isothermal plug flow reactor or PFR is shown to be significantly more efficient compared to a CSTR. Based on our analysis, the PFR only requires a reactor volume of 3.99 cubic meters, whereas the CSTR requires 15.8 cubic meters to achieve similar performance. At the same time, the PFR achieves a high carbon monoxide conversion of 83.3% and produces 855.24 kmol per hour of methanol. Additionally, the selected operating condition of 300 degrees Celsius and 90 bar combined with a short residence time play a key role in ensuring high conversion while maintaining catalyst stability. This condition also allows efficient heat recovery from the isothermic reaction, resulting in a highly productive and energy efficient system overall. Moving on to the separation process part, the combination of a flash separator followed by an adsorption system is found to be effective in removing unreacted gas and impurities. This enables the final product to meet the industrial requirement of at least 99.5% methanol purity. This of molecular CYP3A is particularly important as its specific pore structure allows for highly selective removal of water, which is the main impurity in crude methanol. Finally, the implementation of a dual-column temperature swing absorption system enables continuous operation by alternating between absorption and regeneration cycles. In conclusion, the system provides an efficient, reliable, and industrially feasible approach for methanol production and purification.